Good morning, students. In the last class of the chapter Chemical Kinetics, we discussed about the rate of chemical reaction, different types of rate operation like your average rate, instantaneous rate. Also, we discussed how we can express the instantaneous rate of variation and also how we can express the average rate of variation. We discussed about the different factors affecting the rate of a chemical reaction. How the rate of the reaction is affected by nature of the reactants, temperature, characteristic, surface area of the reactants, radiation, and lastly we discuss how the rate of a reaction depends upon the concentration of the reactants. And we gone through the law of mass action, where we discuss how the rate of reaction is depending upon the concentration of the reactants. And according to the law, the rate at which substance react is proportional to its active mass, and the rate of a chemical reaction is proportional to the product of the active mass of the reacting substances that we discussed in the last class. And accordingly, we derive when if we have the A plus B gives us the product. Okay, and according to law of mass action, okay, rate of reaction are proportional to what A into B, or R equal to what K A into B. Okay, so this is called what law of mass action. Now, today we will discuss about the molecularity, rate law, order operations. First of all, what is your molecularity? Actually, whenever a chemical reaction is going on, the reacting molecules are colliding with each other, so that their bonds will break, and after that the new bonds will form. And the number of molecules that simultaneously collide at one time to bring about the chemical reaction is known as the molecularity of that particular reaction. Okay, so in a chemical reaction, the total number of molecules which simultaneously collide to bring about the chemical reaction. And here one thing remember, if the reaction proceeds only in one step, in that step how many molecules are colliding with each other to bring the reaction, to bring about the chemical reaction, that is called the molecularity. And if we have a complex reaction, that reaction involving more than one steps, then what we are doing? We are calculating the number of molecules taking part in each step of the reaction, and we are calculating the molecularity for each step. As a whole, the complex reactions or those reactions which, that means those reactions which are taking place in several steps, the molecularity has no meaning. The molecularity is always calculated for a single step reaction or a single step of the complex reaction. Okay, and this molecularity we can calculate simply from the law of mass action. Here you see, if this is the reaction, so A plus B gives product, and here we have R is equal to K into active mass of A and active mass of B, that is what molar constants of A and molar constants of B this is law of mass action, then this indicates that in the elementary step of the reaction, so 1 mole of A and 1 mole of B are participating. 1 molecule of A and 1 molecule of B. That means here the molecularity value A power 1 here, B power 1 here. So 1 plus 1 equal to 2. Okay. So molecularity of a particular reaction, that means this single step reaction or a single step of a multi-step reaction, we can calculate from the law of mass action for that step. So here for this reaction, so I have written here the R equal to K into A into B. That means two molecules A and B are participating, are colliding with each other. Okay, and hence the molecularity value 1 plus 1, that's 2. And this molecularity of a reaction is always a whole number. That means in a chemical reaction, okay, at least one molecule or two molecule or three molecule must collide. If molecules will not collide, then the reactions will not happen. Reaction is occurring means at least one molecule is colliding. That means the molecularity will be at least 1. It can never be 0. It can be never be 0. It may be 1, 2 or 3, and more than 3 values is not possible. With at a time simultaneous collide of more than 3 molecules is a rare phenomenon. That's why we are saying that the molecularity never exceeds 3. It's always a whole number. It never becomes 0. Okay. Now this molecularity, let's see. If I take a chemical reaction, so suppose I take N2O5, will give you N2O4 plus half O. So for this reaction, so if I write law of mass action according to law of mass action, R equal to K N2O5. The law of mass action. That means here the molecularity is 1. It's called unimolecular reaction. Called unimolecular reaction. That means if in a chemical reaction, so one molecule is colliding, it is decomposing to bring about the chemical reaction. That's called a unimolecular reaction, and the molecularity here is 1. Similarly, if I suppose CH3 COO C2H5 plus Na also, okay, we will write CH3 COO Na plus C2H5 OH. Here I can write law of mass action R equal to K CH3 COO C2H5, okay, into NaOH. Now we see here the two molecules, this one and this one are colliding. That means here the molecularity 2. Okay. Similarly, if I take NO2, suppose NO plus O2, NO plus O2 is 0, NO2, NO plus O2 is your NO2, 2NO2. Okay, so 2NO plus O2 is 2NO2 gas. Here I can write R equal to K NO square O2. Law of mass action. That we see here molecularity equal to 2 plus 1 equal to what? 3. Okay. So if one molecule is participating, it's a unimolecular. If 2 are decomposing, bimolecular. If 3 are colliding, then trimolecular. Okay. So it's what is a trimolecular reaction. Okay. Now, and this molecularity of the reaction is a theoretical one, and we are calculating from the law of mass action, which we are obtaining simply from the balanced chemical equation. Okay, so the molecularity is the sum of the exponents to which the reacting terms are raised in the law of mass action as per the balanced chemical equation. Okay, now we'll go for the rate law. Rate law. See, whenever a chemical reaction is going on, we are taking certain amount of reactants, certain molecules, and we are writing the equation as per the balanced chemical equation. We are writing the law of mass action. But the thing is actually not that. Suppose now, for a hypothetical chemical reaction, so if A of A plus B of B, if I take what? If I take what product, here I have taken A mole of A and B mole of B. So I have taken A mole of A and B mole of B. This means not that the entire mole of A mole of A, and entire B mole of B will react and will bring about the chemical reactions. When we say A mole of A and B mole of A, these molecules will collide. This means not that all the molecules, all the collisions will be effective, and all the collisions will lead to give the product. That is not mandatory. Some molecules may bring about the chemical reactions, some may not also. So, what is the actual number of molecules which are participating in the chemical reaction? That we can determine when the reaction is going on. When we will allow the reactants to react, we will analyze the product and we will analyze the remaining reactants. Then only we decide that how many molecules have actually taken part in the chemical reaction. That means we can determine it through the experiments. So by doing the experiments, we can determine how many molecules are actually participating in the chemical reaction, and accordingly we can write an equation that is called rate law equation. So you see, if from the A mole of A and B mole of B, suppose what do M mole of A, M of A, and N of B. Suppose M mole of A and N mole of B are actually participating in the chemical reactions. Okay, so actual number of molecules participating in the reaction is N of A and M of A and N of B. Then what I can write? R is equal to K A power A into B power B, and again I can write what? R is equal to K A power M into B power N. So two equations I can write here. One is what? The actual number of molecules which we have taken in the chemical reaction, the balance chemical equation. This is called what? Law of mass action. Law of mass action. So law of mass action we are writing simply from the balanced chemical equation. Okay, A and B. But out of this A and B, actually M mole of A and N mole of B are participating, then I can write R equal to K A power M B power N. This is called what? Rate law. And this rate law is what? Experimental. By doing the experiment only, by taking the data from the experiment only, we can write this is rate law. So rate law is experimental. Means law of mass action is theoretical. Okay. Now see, for example, if I take a reaction so like your S2 plus Cl2 H nu 2 HCl. Okay, here I can write R is equal to K H2 Cl2, H2 and Cl2. This is the law of mass action. Law of mass action. Now R is equal to K has to 0 Cl2 0. Or rate law. Now we see when H2 and Cl2 are reacting in presence of water H nu, a photochemical reaction, so we are getting this HCl, and this we are writing R equal to K H2 and Cl2, called your law of mass action simply from the balanced chemical equation. Now here the rate of this chemical reaction so is not depending upon the concentration of this H2 and Cl2. Okay, because the rate of the reaction so is not depending upon the concentration of H2 and Cl2. That means when we are changing the concentration of H2 and Cl2, the rate is not changing. Experimentally it is found that in this reaction so if we change the concentration of the H2 and Cl2, then the rate of the reaction is not changing. That means the rate of variation is not depending upon this H2 and Cl2. H power 0, Cl power 0. So this is the experimental, okay, and this is called what rate law. So what the rate of variation so R equal to K H to 0, Cl to 0. This is called what rate law. So sometimes for a particular reaction, the law of mass action and the rate law are same. Sometimes it is different also. For example, if I take this N2O5, you should know N2O4 plus half O2 are equal to K N2O5, you know law of mass action, and again R is equal to K N2O5 rate law. So when we are taking the reaction N2O5 R equal to K N2O5, and if we are doubling the concentration of this N2O5, then rate becomes double. So if you make it 2 times, it becomes rate becomes 2 times. That is what the rate depends upon concentration of only one reacting term N2O5. So here the rate law and the law of masses are both are equal. Okay. And here it's not equal. Okay. Now we see whenever a particular chemical reaction is going on, the reacting molecules are colliding with each other to bring about the chemical relationship. Okay, and that the total number of molecules which are simultaneously colliding to bring about the relationship, okay, is called molecularity, and that we can determine from the law of mass action. But whenever we are carrying out the chemical relationship, what are the actual number of molecules who are determining the rate of relationship, that we can determine, and that we can express in the form of rate law. And the total number of molecules which are actually changing during the course, changing the concentration during the course of the reaction, is called what? Order of the reaction. It is called what? Order of the reaction. So what is the order? Order of reaction is the sum of the exponents to which the reacting terms are raised in the rate law. Okay, so for example, if I take A mole of A plus B mole of B is giving the product. Here, law of mass action is what? R is equal to K A power A into B power B. Okay, so your molecularity is equal to A plus B. Okay, now if the actual change of concentration of A is M and B is N, then the rate law is R is equal to K A power M into B power N. So here order equal what? M plus N. This is what you know? Experimental. What? Experimental. So because the rate law is experimental, so and we are determining the order from the rate law. Okay. is the rate law, and A power m, B power n, mn plus n bar. So order of the sum of the exponents to with the rate terms are A0 including rate law. Okay. Now this order is experimental. Okay. What is molecularity is your theoretical. Okay. Now if the order of the reaction, if only one concentration term is changing during the course of reaction, the order of the reaction is 1, it's called first order reaction. If the concentration of two reacting terms are changing during the course of reaction, it is called what? Second order reaction, or is 2. And if the concentration of three reacting terms are changing during the course of reaction, it is called what? A third order reaction. And sometimes what happens, the rate of the reaction not depending upon the constants of any reactants. At the argument, the order is 0. If the rate of the reaction is not depending upon the constants of any reactants, that is called what? 0 order reaction. Sometimes the rate of the reaction also becomes a fraction. Okay, so if you compare the molecularity is always a whole number, but order can be whole number, can be 0, can be fraction also. Okay, and the molecularity we can obtain from the law of mass action, but the order we can obtain from the rate law. Molecularity of the reaction is so if you compare the order and molecularity, so what you can say, the molecularity of a reaction is a theoretical one and the order of a reaction is a experimental one. The molecularity of reaction we are determining from the law of mass action, and order of reaction we are determining from the rate law. Molecularity of reaction is always a whole number, it never becomes 0, and order of reaction can be whole number, can be 0, and even it can be fraction. The molecularity we are always determining for a single step reaction. Okay, and also for multi-step reactions we are determining only for a single step. Let me see, for each step we are determining the molecularity in a multi-step reaction. But order of reactions we are determining overall. And see, order of reactions we are determining from the rate law, and rate law we are taking for the rate determining step, and the rate determining step is the slowest step in a chemical reaction. When we are having a multi-step reaction, so we are choosing the slowest step reaction, and from this slowest step we are determining the order of reaction. Okay, so let us see different kind of examples of your molecularity and order, and how we are expressing the law of mass action, and also how the rate law. Let's see. Suppose we have a reaction of what? N2O5, this what? N2O4 plus half O. Okay, if I write law of mass action R equal to K N2O5. Okay, therefore molecularity equal to 1. Okay, now rate law R equal to K N2O5 experimental. Okay, so order equal to 1. So here the order and molecularity both are same. The rate law and law of mass action both are same. And such type of reaction is also called what? Elementary reaction. Okay. Number 2, if I take CH3 COO C2H5 plus NaOH CH3 COO Na plus C2H5OH. Law of mass action R equal to K CH3 COO C2H5 and NaOH. So molecularity 1 plus 1 equal to 2. Okay. Here rate loss are equal to K CH3CO C2H5 into NaOH. So here order equal also 1 plus 1 equal to 2. Okay. Now next one, 2NO plus O2 gives 2NO2. Here law of mass action R equal to K NO square O2. So molecularity now equal to 2 plus 1 equal to 3. Rate law is also R equal to K NO square O2. So order equal to 2 plus 1 equal to 3. Number 4. Suppose H2 plus Cl2 HNu 2 HCl. Okay. Law of mass action R equal to K H2 Cl2. So molecularity 1 plus 1 equal to 0. Okay. So this rate law is what? Experimental. Okay. Now rate law for this equation R is equal to K has to power 0 C to power 0. Therefore order is equal to 0. Experimental. Okay. Now number 5. If I take what H2 plus Br2 2HBr, H2 plus Br2 2HBr. Here law of mass action R equal to K H2 Br2. Okay. Therefore molecularity equal 1 plus 1 equal to 2. Okay. Rate law R equal to K H2 into Br2 1 by 2. Experimental. Whatever experimental. Okay, so order is equal to 1 plus 1 by 2 equal to 3 by 2. Okay, similarly number 6, we take suppose CH3COO CO5 plus HOH, water in acidic medium, we got CH3COHO plus C2H5OH. Okay, law of mass action, R is equal to K CH3CO C2H5 into H2O into H2O. So here molecularity equal to 1 plus 1 equal to 2. Okay, now the rate law is what actually R is equal to K CH3COO C2H5 into H2O. See here in this situation, so the rate is depending upon CH3CO2H5 and also water, but the concentration of water is in large excess, so but the change in concentration of water is not noticed, is not observed. That's why we can say what the rate is depending upon only the concentration of CH3CO C2H5. So this relation so is assumed to be second order because here you see the rate is depending upon the CH3CO C2H5 and also H2O. Okay, the rate was assumed to be depending upon this one and also water, but because here in this relation so water is taken in large excess. Okay, so small change in concentration of water is not observed. That's why this is called pseudo first order reaction. Okay, so here order equal to 1 is equal to pseudo first order reaction. Okay, so those chemical reactions where the order is assumed to be 2, the rate law, but it is 1 here, it's called pseudo first order reaction. Okay, so these are the different examples of reactions of different order and different molecularity. Okay, now we discuss about the unit of rate constant. What is the unit of rate constant? So we know the R is equal to, even in A gives P product, now R is equal to K into A. Okay, suppose I will take N of A. N of A is what product. When I have N of A giving product, then R equal to dx by dt is equal to K into A power N. That means N times A is taken. Therefore, K is equal to R by A power N. Okay. Therefore, unit of K is equal to unit of R divided by this A is value. This is your concentration. Okay, concentration concentration power n. Okay, now see, unit of k is equal to unit of r equal to dx by dt, that is what concentration per time. What is it? Concentration by time divided by what? Concentration power n. So what I can say? Therefore, unit of k is equal to concentration power. Here 1 is then 1. Now this becomes what? Minus n. 1 minus n into time inverse. So unit of k is equal to what? Concentration power 1 minus n into time power minus 1. Okay. So if the concentration is in mole per liter, then mole per liter power 1 minus n. Here n is what? Order of the reaction. What is n equal to what? N equal to order of reaction. Okay, so if concentration equal to mole per liter, okay, then unit of k is equal to mole per liter power 1 minus n in time your second. Okay, so if concentration is expressed in mole per liter, then unit of k will be what? Mole per liter power 1 minus n into second inverse. Okay, now if so for gaseous reaction, so the concentration are expressed in terms of partial pressure, that in atmosphere. So here unit of k equal to atmosphere power 1 minus n into second inverse. Okay, so when we have the gaseous reaction, so the unit of k is what? Atmosphere power 1 minus n into second inverse. And when we are having the molar concentration, then what? Unit of k equal to mole inverse power 1 minus n into second inverse, where n is what? Order of the reaction. Okay, now let's see. Suppose we have question, find out the unit of k for the relation of order was here 1, 0, 2, 1 by 2. Okay, minus 1 by 2. Suppose. Okay, let's see how we can find it. N here order n. Okay, now unit of k equal to mole liter inverse power 1 minus n into what? Second inverse. Let's see. So here, if I take order A, order is 1. Order consider mole liter inverse power 1 minus 1 into second inverse. Because what? 0 equal what? Second inverse. Here B 0 Means what? Mole liter inverse power 1 minus 0, okay, into second inverse. That is what? Mole liter inverse second inverse. So here one thing you mark here, we have R equal to ds by dt. Now you see moles per liter per second. Unit of R is what? Ds mole per liter, then dt per second. So unit of R is what? Mole liter inverse second inverse. Here also we see for 0 order mole liter inverse second inverse. That means see the unit of rate constant of 0 order radiation is equal to the unit of rate. Okay. Now 2 B C is your 2. So mole liter inverse power 1 minus 2 into second inverse. What mole liter inverse power minus 1. What mole inverse liter second inverse. Okay. Similarly 1 by 2 D. Here 1 by 2. So what happened? Mole liter inverse power 1 minus 1 by 2 second inverse. What is 1 minus 1 by 2 is what? 1 by 2. So mole 1 by 2 liter minus 1 by 2 into second inverse. Okay. Now minus 1 by 2. Minus 1 by 2. So what? Mole liter inverse power 1 minus 1 by 2 into second inverse. So what? Mole liter inverse power 1 plus 1 by 2. What? 3 by 2 second inverse. That means what? Mole power 3 by 2 minus 3 by 2 into second inverse. So in this way we can find out the unit of rate constant of reactions of different order. Simply you put the formula. Okay, mole liter inverse power 1 minus n into second inverse, where n is the order of the reaction. Okay. Similarly, we can say question number 2 if I write. Okay. Find out the unit of K for the gaseous reaction, for the gaseous reaction. So you know A1 B3 or C 3 by 2. Okay. Now say order n. Unit of K equal what? Atmosphere power 1 minus n into what? Second inverse. So order 1. So unit of K what? Atmosphere 1 minus 1 into second inverse equal what? Second inverse. This is equal to 0. Now 3. So atm atmosphere power 1 minus 3 second inverse what? Atmosphere minus 2 to second inverse. 3 by 2 atmosphere 1 minus 3 by 2 into inverse. Okay, is equal to atmosphere. So 1 minus 3 by 2. Okay, that is what? Minus 1 by 2 second inverse. Okay. So these are the ways how can you find out the unit of rate constant for a first order, 0 order, second order, third order, and even if a fractional order reactions. Okay. Now another question can say Let's say concentration H2O2 gives H2O plus O2. 2H2O2 gives what? 2H2O plus O2. Okay? 2H2O2 gives 2H2O plus O2. Now this reaction occurs in two steps. Okay? Step 1. H2O2 gives H2O plus O, slow. Step 2, O plus O, O2, fast. Okay? Determine order of reaction. This is the question. Question what you 2H2O2 giving what? 2H2 plus O2, and this reaction process in two steps, and we have to find out the order of the reactions. Now order of the reactions we can find out from the rate law, and rate law we write from the rate determining step, and rate determining step is the slowest step of the multi-step reaction. But here this reaction is consisting of two steps. So this is the slow step, this is the first step. So from the slow step we will write the rate law. Okay. So from the slowest step, H2O2 gives H2O plus O. The rate law is R is equal to K H2O2. Okay, therefore order is equal to 1. Because in the rate determining step, in the rate law, R equal to K H2O2, one single term is there, so the order will be 1 here. Okay, so these are all about the order and molecularity of a particular chemical reaction. So okay, so in the next class on also we will discuss about the kinetics or the integrated rate expression for the reactions of first order as well as second order. Okay, thank you.